We're going to continue our discussion of two-sample tests. You remember last time we talked about two kinds of two-sample tests. The two-sample z-test that we used for testing differences between means, and also the two-sample proportion test that we used for testing differences in proportions in two samples. This time, we are going to be looking at what is called a t-test. What is the difference? When I taught you about z-tests and proportion tests, I said that I'm teaching you at the same time because they both use the same underlying distribution, the normal distribution. The advantage of using a normal distribution is that the critical value that we'll use for all of our t-tests, the standard of significance at 0.05, is always going to be 1.96 for a two-tailed test. We can look at both of these tests and we're going to get exactly the same type of critical value. That makes things simpler. But to use a normal distribution, we need to know something about the population. We need to know the standard deviation of the population, and most of the time we don't know that. However, when we have a sample, we can extrapolate from the sample to the population, and that's going to be the technique that we'll use for our z-test. You may remember me telling you that for any population, what is true of that population should be true of any sample drawn from that population. Therefore, if we don't know anything about the population, we can take what we learned from our sample, we can extrapolate that back to the population. What is true of that sample should be true of the population from which it was drawn. Specifically, the mean and the standard deviation. The mean of the sample should be the same as the mean of the population from which it was drawn. And the standard deviation should be the same as the standard deviation from the population. So we can use what we learned from the sample to extrapolate back to the population. However, there's a problem. And that is, if we estimate the mean, if we use the mean of our sample as a point estimator to the population, then when we try to estimate the standard deviation, we are losing 1 degree of freedom in our calculations. Degrees of freedom, n-1. So here's what we do. When we do the calculation for the standard deviation from our sample to the population, we use n-1 in the denominator as we calculate the standard deviation. If you have really large sample sizes, this is just going to be a blip. You'll never notice the difference. However, as sample sizes get smaller, then the n-1, the degrees of freedom that we're using on those smaller sample sizes, can actually have a lot larger influence on our population variance estimates. The takeaway from this is that when we have small sample sizes and we're using a t-test, we need to adjust the degrees of freedom. And I'm telling you this because when we get to this part of the hypothesis test, you're going to see degrees of freedom. And you may wonder, where does that come from? Well, I have a video all about how t-tests, the history of t-tests, and I welcome you to watch that. But for now, if you know that we will use degrees of freedom, n-1, for calculating our critical value, that's all you need to know. We're no longer going to be able to use 1.96 like we did with the z-test and the proportion test. Instead, we're going to use a critical value that will change based upon the sample size. It's always going to be larger than 1.96. All right, so with that, let's talk about two-sample tests. There are two ways to get to two-sample tests. The first is the independent samples t-test, where we have two independent samples, two separate samples, 1 and 2. Now those samples are collected about the same time, and they're each measured once at around the same time. The second way that we can get to a two-sample test is the paired sample t-test. In this case, we actually have the same sample, but we're measuring it twice. The same sample being measured more than once, like the same puppies that are measured before and after. The first of the tests that we're going to tackle is called the independent samples t-test. We're going to be using the t-distribution, we're going to be using samples drawn from a population, and we're going to be looking for whether there is a mean difference in those samples. We want to have a race. So think about the animals that you know that run the fastest. I thought of racehorses and cheetahs. We're going to have a race between the horses and the cheetahs to determine which group runs faster. So what do you predict? Which is going to run faster, the horses or the cheetahs? The answer is it depends on the length of the race. Cheetahs are really fast out of the block. So if it's a short race, 100 meters, the cheetahs are going to win. On the other hand, racehorses have more stamina. They're going to be slower coming out of the blocks, but once they get running, they're going to be able to run for a mile, whereas the cheetahs are going to tire out pretty quickly. Here's the bigger point. If we're going to race the horses against the cheetahs, we are going to start with a population of racehorses and draw a random sample of horses from that population. That's our group for sample 1. Then we'll do the same with the cheetahs. We have a second population of all cheetahs. We're drawing a random sample from that second population, and we want to know whether there is a mean difference between the finish times for these two samples. The independent samples t-test compares means for two groups measured at about the same time. This is also called an independent measures test, or sometimes a between subjects test. We have two samples. The sample of racehorses, this dozen racehorses that we run, are going to have an average finish time, and because they won't all run at exactly the same speed, there will be some variation around that finish time. That will be our standard deviation. We'll have a mean and a standard deviation for sample 1. The same is going to be true for sample 2. The cheetahs are going to have an average finish time, and because not all of the cheetahs run at exactly the same speed, there will be some variation. There will be a standard deviation around that finish time mean for the cheetahs as well. We have a mean and a standard deviation for sample 1, a mean and a standard deviation from sample 2. We're assuming that both are drawn from populations that have the same mean, that the average finish time for racehorses will be the same as the average finish time for cheetahs. We have two independent groups. For our example today, we're going to use our business of the week, and the two independent groups that we're going to be examining will be puppies. We're going to train two groups of puppies, one using clickers, the other using food reward training. Now, a clicker is something that we could use to anchor a behavior. When the dog does what you want the dog to do, you click, and that indicates that there is the behavior is correct. And sometimes you would use food reward, although if we did that in this example, that would be called a confounding variable. We don't want to use clickers and food reward. Clickers only, food reward only. And here is our research question. Mickey is a dog trainer studying reinforcement effectiveness. He randomly assigns 16 puppies to two different reinforcement training techniques. After training the puppies, he measures the number of correct responses by each puppy in 10 exercises. Was there a difference between these two training techniques? Now, I want you to pay attention to the words in blue, because we're going to see another example with our paired sample t-test that looks very, very similar. But the words in blue help to distinguish the type of research design that we're using. We have 16 puppies that have been randomly selected and then randomly assigned to two different groups. Having done this research, we now know the mean, the standard deviation, and the sample size for each of our two samples, and that's what we need in order to do this test. So let's review what we know. Both the clicker training and food reward groups had a sample size of 8. Those groups were of equal sizes, but we can see that the sample mean was slightly higher for the clicker training group than for the food reward group, meaning the dogs in the clicker training group got more tasks correct than the ones in the food reward group. Although those sample means are fairly close together, they're fairly similar. The standard deviation for the clicker training group was a little bit smaller than for the food reward group, and with that, we know what we need to know in order to do this test. I want you to know how to choose an independent samples t-test. You look at your data, you make the choice of what type of test you're going to use. Here are the elements that you'll want to look for when you're making that decision. The independent variable is only 2 samples or groups, so it's categorical. If we have more than 2 groups, we'll be using an ANOVA. The participants in each of those groups are randomly selected from the population. Everyone in the population had an equal chance of being selected. And furthermore, they are randomly assigned to either the clicker training or the food reward group. They are assigned randomly as well, random selection and random assignment. However, with this type of research design, sometimes we create a quasi-independent variable out of naturally occurring independent variable categories. So if people come to us in a certain condition, in other words, they are this, we put them into the group based upon their being this and the other people being that. So we create our 2 groups not based on anything that we have manipulated or controlled, but on the pre-existing characteristics of those individuals. That's called a quasi-independent variable. It's functioning like an independent variable, but we didn't manipulate or control that. We're just taking them as they come. The sample sizes should be roughly equal. Now, what does roughly equal mean? You divide the largest sample size by the smallest sample size. That ratio shouldn't be greater than 1.5. If it is, we may need to do more data collection. It can lead to problems with interpretation or getting results that are not valid. The dependent variable is at the scale level. We're measuring number correct out of 10 tasks, so our scale level runs from 0 to 10. We can create a mean for our scale level data. We can calculate the mean from our sample, use that to extrapolate back to the population value. We do the same thing with our standard deviation, but because we do not know the standard deviation of the population, we're going to have to estimate that from our sample. We'll lose 1 degree of freedom, and that's where we will be using our t-distribution. There are some assumptions for the independent sample t-test that we want to check, make sure these assumptions have been met. If the assumptions have not been met, we have a greater chance for making a type 1 or type 2 error. So in order to assure that we are getting the best results possible, we want to check for these things about our independent and dependent variables. The first is we want to check our dependent variable and look for outliers. We shouldn't have any extreme outliers. Outliers create leverage. They can cause one group to be artificially high or artificially low and distort the findings. Second, no missing data. We want to be sure that we have a complete data set. In a data set that's relatively small, like the one that we'll be using, if we had missing data, we simply wouldn't have any information for that particular puppy, and so they would probably be excluded from the data set. But in a larger data set, we may need to impute what the number would have been if we had that score for a particular individual. And third, independence. The dependent variable data are independent. The scores in one group are not influencing scores in the other group. You remember the story that I told you about the racehorses and the cheetahs? And those groups were independent of one another. The scores from the racehorses weren't changing the scores from the cheetahs. But that's because of the way I did my research design. I ran the racehorses first, then I ran the cheetahs. Why did I do that? Because I was worried about independence. You see, it turns out racehorses might run faster if they're being chased by a cheetah. In other words, if I ran all of the animals at the same time, they might forget, or at least the cheetahs might forget about the race, and they start chasing the horses, which could lead to a variety of problems, including maybe even missing data. Therefore, I want to be sure that there is no way that the scores in one group are influencing the other group. That's what makes them independent. There are some assumptions that we can only evaluate after we have collected the data. The first would be normality. The assumption is that the sampling distribution is normally distributed. And we have a shortcut for determining whether that is the case, and that is that we measure the dependent variable data to assure that they are normally distributed. Typically, we use a Shapiro-Wilk test for this assumption. It's important to remember that the assumption of normality is not that the dependent variable is normally distributed. The assumption is that the distribution of sample means from which that sample is drawn is normally distributed. The problem is we don't have access to that information. So how can we determine whether the assumption of normality has been met? This is where we use a shortcut. We measure the dependent variable to see if it's normally distributed. Because if it is, then what is true of the sample should be true of the population from which it was drawn. If the sample is normally distributed, then it should be drawn from a normally distributed population. And what we know about normally distributed populations is that even for small sample sizes, the distribution of sample means is normal. So we use our shortcut by measuring the dependent variable. If the sample is normally distributed, we can assume that we have a normally distributed population. All is well. If, however, my sample is non-normal, it's skewed or kurtotic, this is where the central limit theorem comes to our rescue. When we have sample sizes larger than 30, and this is 30 for each group, so 30 racehorses and 30 cheetahs, then the central limit theorem assures that the distribution of sample means is normally distributed, and this assumption has been met. And there's one more assumption about the variance for independent samples t-tests, and that is the homogeneity of variance, that the variance in the two groups are approximately equal. This is something that we will test with Levene's test. So we need to talk about this in a little more detail. Homogeneity of variance. That's quite a mouthful, so let's see if we can break down these words and understand exactly what they mean. Homo, same. Geneity, genus, genesis, nature or kind. So homogeneity, same nature or same kind of what? Variance, the variability or the standard deviation in our sample. The same kind of variability, the same nature standard deviation. We are saying that the variances in the two groups are of the same nature, or that the variances are approximately equal. They're not going to be exactly the same, but they're close enough. How do we make that determination? We use something called Levene's test for homogeneity of variances. Now remember, our assumption is that the variances are the same. Hypothesis tests always test for whether the differences are statistically significantly different. So when we do our interpretation, we can look at the p-value for our Levene's test. If that p-value is non-significant, that means the group variances are not the same, or we can assume that they are equal, or at least close enough. In other words, we want to see non-significant Levene's tests. On the other hand, if we look at the Levene's p-value and find that it is less than 0.05, well then that is a statistically significant test. The variances are different and the assumption has been violated. But here's another thing we should keep in mind about assumptions tests. Many times we use a criteria that is more stringent than 0.05. With small sample sizes, we might use 0.05, larger sample sizes, 0.01. With much larger sample sizes, we might use 0.001. It's important that we keep in mind what that significance test is telling us, and many times with larger samples, those differences will be statistically significant, even though they're not as pressing. So what we might do is, as we have larger sample sizes, it become more stringent on the criteria that we're using for determining statistical significance. But here's the takeaway. as long as our sample sizes are greater than 30, and those sample sizes are approximately equal, n1 is approximately equal to n of 2, then the t-test is robust to violations of homogeneity of variance. Robust means that if the assumption is violated, that the test will still give us valid results. We don't have an increase of type 1 or type 2 errors. But with all of these tests, it's important to remember that robustness, we get one shot at that. In other words, if there is one violation of the assumptions, we might still rely on the robustness of the t-test. However, if you have multiple violations, multiple assumptions, or you have really large violations of the assumptions, don't rely on the robustness of the test to make up for that. In that case, we're going to need to do something with the data to make sure that we're getting valid results. Here's another important thing to know about the variance in a t-test. Now, you may recall when we did a one-sample t-test, where we have one sample drawn from a population, we used the standard deviation of that sample to extrapolate back to the population. We used the standard deviation as the denominator in our t-test. With a one-sample test, we use the sample standard deviation to estimate the population standard deviation for the standard error of the mean, which is the denominator in our t-test. But now we're doing two sample tests. Each sample has a standard deviation. Unlike the one-tailed test, where we can simply use the standard deviation of that one sample, if we have two samples with two standard deviations, which standard deviation are we going to use? Well, the answer is we're going to use both. And if the sample sizes are the same, this is going to work very well. We'll simply combine those two standard deviations. However, if the sample sizes are different, then we have a problem. We're going to need to adjust the standard deviation for the size of the sample. This is called pooled variance. We're going to pool the variance of sample 1 with the variance of sample 2, but then adjust for sample size. The pooled variance is the weighted mean of the two samples' variances. So why do we need to adjust the standard deviation by the sample size? Let me give you an illustration to make this make a little more sense. Let's say that we have a glass of 2% milk and a glass of skim milk, which has 0 milk fat. If we pour those two glasses together, the 2% and the 0%, what do we have in terms of the fat content? It's going to be about 1%, because the two glasses are of equal sizes. But what if we have a half gallon of 2% milk and a quart of skim milk? You see, now the combination of these two amounts is not going to give us 1% or halfway in between. It's going to be more heavily weighted toward the 2% side. It'll be more than 1%. So the combination, if we were going to calculate what is the milk fat percentage, would have to weight the 2% milk amount, in this case about twice as much, as the quart amount. This is an illustration of the weighted means, where one gets more weight than the other based upon the larger sample size. Now, to help make this make more sense, I do have some videos that you might want to look at. I have one on pooled variance that explains the pooling of variance. And the good news is the software is going to do this for us. The pooled variance will be calculated as part of our calculations. The second is about unequal sample sizes. What happens if you have unequal sample sizes? Can you still do the t-test? The answer is, well, you could do it, but it would be wrong. It's very likely to be an error. And then the third video that you may want to look at is the Levine's test video about homogeneity of variance. And in this video, I'm able to use some real-world normal distributions or models of normal distributions to kind of illustrate how the overlap between those two distributions actually works. Now we're ready for step 2 of our hypothesis testing process, and that is to establish the null and the alternative hypothesis. The null hypothesis is that both of these samples are drawn from populations whose means are equal. This is based upon the fact that they were randomly selected. Each sample comprises individuals who had an equal chance of being drawn from the population. So the two samples that we randomly assigned should be the same. They should have population means that are equal. And we're going to write that as H sub 0 colon mu1 equals mu2, our null hypothesis. That is really the same as mu1 minus mu2 equals 0, because if two things are the same and you subtract one from the other, the mean difference would be 0. The alternative hypothesis will be H sub 1 colon mu1 does not equal mu2, that these two population means are not the same. And the fact that our null hypothesis says equal and our alternative hypothesis says not equal, that tells us that we're going to be doing a two-tailed test. Select a criteria for statistical significance. And as we often do, we're going to keep our alpha level set to 0.05. However, we could set it to 0.01 or 0.10 or really any other probability value that we chose to use. But if we did so, we would want to justify why we are choosing an alpha level different than 0.05. Then we need to determine what is our critical value, what's our cutoff score, and that is going to be based upon the alpha level of 0.05 and the degrees of freedom. So what is that? I've already told you that degrees of freedom is n minus 1, but that's for one sample. And in this example, we have two samples. It's n minus 1 for each sample. So let me show you two ways that I could write that exact same formula. The first would be n1 minus 1, or the first sample size minus 1, plus n2 minus 1, or the second sample size minus 1. Add those together. Exactly the same formula, n1 plus n2, just add them together and then subtract 2. Either way will get us to the correct number of degrees of freedom. And as we've done for many tests, we're going to assume that we're using an alpha of 0.05 and a two-tailed test. So let me show you how you can calculate the critical value for this independent samples t-test. And to do that, we're going to turn to the spreadsheet that you've downloaded and put on the desktop of your computer. Let's open up the spreadsheet for this week. And we're going to go to the tab labeled CV, T, and P, or critical value, t-test, and probability. The first thing we need to know is the degrees of freedom for our groups. Well, we have two groups of puppies. There are 8 in each group. So if we add 8 and 8, that is 16. The degrees of freedom would be n1 plus n2 minus 2, or 14. So here in the box where it says critical t-value for alpha 0.05 two-tailed test, we can simply enter 14 for our degrees of freedom, and we will get a critical value of 2.145. That's a simple way to do this. Note too that you can change that alpha level from 0.05 to 0.1 or 0.01. You can also change 1 versus 2 tails, and when you do that, it will change your critical value. There is, however, a second way of calculating a critical value, and that would be to use a t-table. Look at the bottom of this spreadsheet. So scroll up a little bit. You'll find this student's t-distribution table. We have two major columns, one for two-tailed test, the other for one-tailed test. We'll be using the columns on the left for two-tailed test. What's our alpha level? 0.05. We'll be using the first column under alpha, 0.05, two-tailed test with 14 degrees of freedom. We work our way down this first column till we get to 14. The critical value is 2.145. And with that, we're ready for step 4. We're going to calculate the test statistic. I've included the formulas that we could use to calculate that by hand. However, for this example, we're going to turn to the statistical software JASP. You have two spreadsheets or two JASP files on your desktop. One is for independent samples, the other is for paired samples. We'll be using the independent samples example for this. We open up a fresh iteration of JASP, and then to open our data set, which should be on your desktop, we'll go to the main menu icon, open, Computer, Desktop. We'll find the data set for the independent samples t-test, and click on that, click to open. Now the first thing that I want to do is point out something about the structure of the data. Notice that we have correct, which is the number correct out of 10, that's a scale level variable. And then we have group, which is a nominal variable for clickers and then for food. Pay attention to the structure of this data. This is how we have to structure our data for doing the independent samples t-test in JASP. And the same would be true for R, for SPSS, for other statistical software. However, in Excel, you will often see the paired sample and the independent sample t-test set up with their data in the same structure, which is a little, well, I'll show you how that works. The point is that you will encounter data sets that need to be restructured. So for instance, if you had an Excel data set with just 2 columns of data, you would need to create a single column of scale level data and then create a categorical column with the names of the groups associated with each of the scores, as you see in this example. All right, so back to JASP. We're going to do a t-test, an independent samples t-test, which we will find under the drop-down menu for t-tests. Under classical, click on independent samples t-test. There's a lot of settings here. Let me show you which ones we're going to be using. First of all, we're going to move our scale variable, correct, into the dependent variables box. And then we're going to move our grouping variable, or group, into the grouping variables box. You always get a hint as to which variable goes where by the ghosted out scale and categorical indicators here in the lower right corners. We're going to do students t-test, but we're also going to get Welch's t-test, which we would use if the assumption of homogeneity of variance was violated, and the Mann-Whitney test, which is a non-parametric alternative to students t-test. Our alternative hypothesis is that group 1 does not equal group 2. You remember that when we set up our null and alternative hypothesis. The alternative, mu1 does not equal mu2. Under assumptions checks, let's get normality, equality of variances, and we'll use Levine's test for this. Missing values, if we had missing values, we would exclude the cases per dependent variable. And then let's go to additional statistics. We've got our location parameter with a 95% confidence interval. We also want to get an effect size. For this, we'll use Cohen's d. We need our descriptive statistics and some plots. Get the descriptive plots and the rain cloud plots with the horizontal display. As you click on those settings, you'll notice that the results appear in the results pane. So let's work through these results in the way that we would if we were doing a test. In other words, we'll start with our assumptions, we'll build upon that information, and then we'll get to actually interpreting the test. We'll start with the assumption check for normality. This is that Shapiro-Wilk test. And what do we see? A p-value of 0.7 that is non-significant. In other words, 74 cents would be greater than 0.05. There is no problem with normality in this test. Then we look for the Levine's test for the equality of variances. And again, the p-value is non-significant. In this case, it's a 0.49. Generally speaking, or always speaking, we want our assumptions tests to be non-significant because the assumption test is testing for differences. We don't want differences. The assumption is that they are the same. The variances are the same, that the sample sizes are the same. If we're testing assumptions, we want our data to meet those assumptions. We don't want our data to be different than the assumptions. We don't want statistically significant assumptions tests. We want non-significant assumptions tests. Now, it doesn't really matter what we want. If this test is significant, we've got to do something about it. But I want you to have that mindset. Assumptions tests we would prefer to be non-significant, and then usually we're looking for statistically significant findings for the means tests. The descriptive statistics are going to be used in our write-up. So we'll have our sample sizes, the mean, and the standard deviation. Those will be the most important parts that'll go into our APA-style write-up. Now let's take a look at the plots. In this plot, we can see the mean and the confidence interval for both groups, and you'll notice that the mean of the clicker group is captured by the 95% confidence interval of the food group. In other words, they're slightly different, but not different enough to be really different. This is a non-significant difference. We can also look at the other plots that are given to us. So for instance, the rain cloud plots. This is going to display your dependent variable, and it'll do it in different ways. We have the horizontal setting versus the default vertical setting. In a rain cloud plot, the dots represent the actual scores. And here we have a number line running from 0 to 12 in this case, showing us where those dots fall. We have a box plot representing the distribution of the dots, the raw data. And then we have overlapping distributions for each of the groups. And notice they're color-coded, in this case, green and orange to delineate which group is which. In the horizontal data, we see exactly the same idea. This gives us a hint as to what our data look like. They're close enough to normal. They're distributed in a way where the group means are really not different from each other. Now, we are ready to look at the findings from our independent sample t-test, and we're ready to start interpreting those findings. So let's go to the independent samples t-test table, and you'll notice that we have the 3 types of tests. We're most interested in students' t-test, but I've included the Welch and the Mann-Whitney so you can see the differences in these tests. Because the assumption of homogeneity of variance was met, the students' t-test and Welch's t-test will have very similar findings. For instance, the t-statistic is the same for both. It's a 1.587. Now remember, our critical value was a 2.145, and that 1.5 hasn't made it over the fence of 2.145. A difference that you will find between students and Welch's test will be the degrees of freedom. Students' test degrees of freedom is the n1 plus n2 minus 2, or 14, whereas Welch uses a more complicated formula. 13.45 is the answer for that, although many times we'll simply round that up or down to the closest whole number. So it does end up being similar to students' t-test in that sense. The probability value. We're looking for probabilities less than 0.05 for statistical significance. And for students' t-test, we have a 0.13. 13 cents is not less than 0.05, non-significant. When we look at our confidence intervals, we see the lower interval is negative, the upper interval is positive. It crosses 0. Our null hypothesis was that there was no difference, 0 difference between these two groups. So the fact that the confidence interval crosses 0, the p-value is greater than 0.05, our test statistic is not over the fence. All of that tells us the same thing. These are non-significant findings. However, there's one more thing that we want to talk about, and that is the effect size. So notice the effect size is a 0.79, which is really close to 0.80. That's a large effect size. Here's how I would do the write-up. T with 14 degrees of freedom equals 1.59, a p-value of 0.14, 95% confidence interval, and my effect size. All of this tells me that this is a non-significant test. Now, before we go on with the interpretation, I do want to show you how we can do both student's t-test and Welch's t-test using Excel. And for this, we're going to go back to our Excel spreadsheet that I created for this course. You will see that on your desktop. Now we're going to be looking at the Tool Pack tab. So find that tab and let me walk you through the steps for doing these two tests in Excel. In order for this to work, you need to have the Analysis Tool Pack installed, which we do, and if you have any trouble with that, just let me know and I can help you with the installation. But I'll assume we have that installed because we've done that in previous examples. Go to the ribbon and click on Data. You notice over here on the right, we have Data Analysis. That's what we're looking for. Click on the Data Analysis, and then from the Data Analysis options, choose which type of test you want to run. We're going to run Student's t-test first. This is t-test to sample, assuming equal variances. In other words, we have looked at our Levine's test and the variances are the same. The assumption of homogeneity of variance has been met. Click OK. Now we're ready to fill in some information. For our variable range 1, we'll get the information, the data, in column B. For variable range 2, get the data in column C. Our hypothesized mean difference is 0. Both of these samples are drawn from populations whose means are the same. There is no difference. We'll keep our alpha level at 0.05. And for the output range, click on G4 and then click OK. Now, before we interpret student's test, let's also do Welch's t-test. You'll see that the steps are very, very similar, but then we'll be able to compare the output for both of these tests. Returning to our Excel spreadsheet, click on the Data tab in the ribbon, and then Data Analysis. And this time, for the Welch's t-test, the sample variance is not assumed to be equal. So we'll choose that t-test, that's for Welch's, and then click OK. From here, the setup is pretty much the same as we've used previously. For our variable 1 range, column B. For variable 2, column C. Again, the hypothesized mean difference is 0, and the alpha level is 0.05. This time our output range is G20. And now click OK. We can see the findings for both of these tests. They're similar, but there are some distinct differences. Let's do a little comparison to find out what those differences are. For the student's t-test, the mean, the variance, and the observations is exactly the same as the mean, variance, and observations for Welch's t-test. That also means that the mean difference is going to be the same. That's because these are exactly the same data points. You will notice that in the student's t-test, the pooled variance has been calculated, and that is not calculated for Welch's t-test. However, the hypothesized mean difference is 0 for both tests. Degrees of freedom, 14 for student's t-test. But notice how with Welch's t-test, they calculated that complex formula for degrees of freedom and then simply rounded it down to 13. After that, the t-statistics are going to be the same. That's for this particular test. If we had a test where the variances were not equal, then you would see a difference in those t-statistics. And we're going to be using a two-tailed test. The probabilities, again, very, very similar because the assumption has not been violated. And then finally, the critical values, a slight difference in the critical values. And that's, of course, based on degrees of freedom, where our student's t-test is using 14 degrees of freedom, giving us a critical value of 2.145. In the Welch's t-test, still using the same t-table, same t-distribution, but with 13 degrees of freedom, the critical value is 2.160. And that's how you can do both of these tests using the tool pack in Excel. Now we're ready for step 5. Let's interpret the results and write up the findings. There are three ways that we can determine statistical significance. The first is whether our test exceeds the critical value. And in this example, the test findings are not over the fence. They are not statistically significantly different. The second way that we can interpret is look at our p-value and see if it is less than or smaller than 0.05. And we see that no, it is in fact greater than 0.05. And we're looking at a mean difference of 0. Is that included in our confidence interval? Well, the lower is negative, the upper is positive, so yes. The confidence interval includes 0. All of this telling us the same thing. This test is non-significant. We do not reject the null hypothesis. Although at this point, something's bugging me. And that is the effect size. Remember, the effect size was huge. It was a 0.79. That is a large effect size. And yet, this test was non-significant. How is it that we missed that effect? It should have been easy to find. Well, I'm going to solve that mystery a little later on. But for now, just sort of think about that. We have a large effect size, which should be easy to identify, and yet we missed it. Is that a type 2 error? We're going to find out. Here's how we would do our APA-style write-up. We'll first start with the tests that we did. An independent samples t-test was conducted to determine whether puppies trained with clickers performed better on exercises than dogs trained with traditional food reward training. A group of 16 puppies was divided into two groups. The first group was trained using clicker training, and the second group was trained using food reward only. Remember, the way that I'm designing this APA-style write-up is I want it to be sufficiently detailed that you could replicate my findings. You could repeat the study that I did, and you would get results. Hopefully your results match up with mine, but if not, we're still going to learn something. We have to determine why those differences exist. The whole point of this write-up is to give you adequate information to replicate the study that I did. Now I'm going to mention the assumptions tests. Two reasons to do this. One, it's the right thing to do. We want to show that these assumptions have been examined and the results are going to be valid or have a greater chance of validity than if we hadn't checked for those assumptions tests. And the other is to show that we know what we're doing. When I do reviews of articles that are sent to me from a peer-reviewed publication, that's one of the things I look for. Did you do the assumptions checks? And did you document that you did the assumptions checks? I want to know that you have done those because that's a really quick indicator that you know how to use these statistical tests. If you're skipping the assumptions test, I'm going to start looking really closely at the numbers because something could be wrong. Preliminary data screening showed that scores in both groups met the assumptions of normality with the Shapiro-Wilk test. Levine's test was non-significant, indicating the assumption of homogeneity of variance had been met. And now the full write-up, the groups did not differ significantly. T with 14 degrees of freedom, I have the probability, the confidence interval, and the effect size. The mean for the clicker training group, notice the mean and standard deviation included there. I'm using M for mean and SD for standard deviation per APA style. So the mean for clicker training was not statistically significantly different than for food reward training. Again, the mean and the standard deviation for that group, despite Cohen's D large effect size. These findings do not support the idea that clicker training is more effective than traditional food reward training. So now you know how to conduct an independent samples t-test, how to run the stats, how to interpret, how to write up the findings. That is the first of the two sample tests that we're going to learn. What is the second of the two sample tests that we're going to learn? It's called a paired samples t-test. It's where we have the same group being measured more than once. So let's learn about this paired sample t-test.